In physics, work is said to be done when a force acts on an object and the object moves through a distance. The work done by a constant force is defined to be the product of the magnitude of the displacement and the component of force parallel to the displacement. Let's say an inclined force acts on a block and moves it through a horizontal displacement d. The component of the force parallel to the displacement is given as F cos theta. And so our work done is going to be equal to the component of the force parallel to the displacement multiplied by the displacement. And so we get Fg cos theta as our work done. The physical quantity work is a scalar quantity and it has no direction, only magnitude, which can be either positive or negative. And the SI unit of work is Newton meter or joule. Suppose we have a varying force acting on an object over a distance, and let's call this distance x. We can divide our distance or interval into very small segments, each of length dx. And we make these intervals small enough so that the force is approximately the same over each interval. And so we can calculate our total work done as approximately equal to the sum of the work done over all the intervals. So approximately our work done is equal to F1 dx1 plus F2 dx2 plus F3 dx3 plus F4 dx4 and so on until we get to our final interval. We can write this using the summation notation as Fi dxi from I equals 1 to n, where n is the number assigned to our final interval. Remember that we made our intervals small enough that the force is approximately the same over each interval. This means that the smaller our interval, the more accurate our result gets. If we take the limit of our sum as our interval dx approaches 0, we get the most accurate result possible, which is the actual value of our work done. And this is equal to the integral of our force F over our displacement x from x0 to xf, where x0 is our initial displacement and xf is our final displacement. Let's say we have a crate pulled by a string having a tension of 15 Newton. Now this string is inclined to the horizontal at an angle of 15 degrees and the tension in it remains constant throughout the duration for which it pulls the crate. Let's also say it pulls this crate for a distance of 20 meters and we want to find the work done in pulling the crate through this distance. The horizontal component of the tension in the string gives us our parallel component of force, and that is equal to 50 cos 15, which gives us 48.3 Newton. Our work done therefore is going to be the parallel component of force multiplied by the distance through which the crate was pulled, which gives us 48.3 multiplied by 20, and this is equal to 966 joules, which is the work done by the string in pulling the crate. Let's consider a second case where the crate is pulled by an elastic spring instead of a string, and the elastic spring gives a varying force over the distance through which it pulls the crate. We want to find the work done by the spring in pulling the crate from an initial point where it has a displacement of 20 meters from the wall to a point where it has a displacement of 5 meters from the wall. And let's assume the varying force provided by our spring is equal to 50 into 1 minus 0.05x, where x is the displacement of the crate from its starting position. At the initial position, our x is equal to 0 meters, and at the final position, our displacement from its starting point is going to be equal to 15 meters. We know that the work done by a varying force is equal to the integral of the force over its displacement from its initial displacement to its final displacement. And so the work done by our spring is going to be equal to the integral of 50 into 1 minus 0.05x from a displacement of 0 meters to a displacement of 15 meters. Evaluating the integral gives us 468.75 joules as the work done by our spring in pulling the crate. Within the scope of this video, we can define energy simply as the ability of an object to do work. We can think of kinetic energy as the energy a body or an object possesses due to its motion. The kinetic energy of a particle of mass m traveling with a speed v is given as half mv squared. To see the relationship between work and kinetic energy, let's consider a particle of mass m moving with an initial velocity vi, which is acted upon by a force F. This force F acts on the object through a displacement x and gives it an acceleration, changing its velocity from vi to vf, where vi stands for initial velocity and vf is its final velocity. Using the third equation of motion under constant acceleration, we can write that vf squared equals vi squared plus 2ax. And so rearranging this, we can write that ax equals vf squared minus vi squared divided by 2. If we multiply both sides by m, we have max on the left hand side and half mvf squared minus half mvi squared on the right hand side. From the definition of force, we see that ma equals our applied force F. And also from the definition of kinetic energy, we can see that half mvf squared equals our final kinetic energy of the object and half mvi squared equals our initial kinetic energy of the object. And so we can write Fx equals Ke final minus Ke initial. Fx is our force multiplied by the displacement of the object, and so it's equal to our work done. Therefore, we can write work done equals Ke final minus Ke initial. This equation is known as the work energy principle, and it can be stated in words as the net work done on an object is equal to the change in the object's kinetic energy. We can think of the potential energy of an object as the energy associated with forces which depend on the position or configuration of the object relative to its surroundings. We have various types of potential energy, but we're only going to discuss gravitational potential energy in this video. To do that, we first have to talk about conservative forces. A force is said to be conservative if the work done by it or against it in moving an object does not depend on the object's path. This means that the amount of work done only depends on the initial and final points of the object. A common example of a conservative force is the gravitational force. If an object falls from rest through a vertical height under the action of gravity, the work done, irrespective of the path taken, is given as mgh. Mg is the weight of the object or the gravitational force acting on the object, and h is the distance through which it moves. This means that when at height h, the object has the ability to do work equal to mgh. And so we can define the gravitational potential energy of an object as the product of its weight and its height above the Earth's surface. If, for example, the object is moved from an initial height, h1, to a second height or a different height, h2, our work done is going to be equal to mg, its weight, multiplied by the distance through which it moves, which is equal to h1 minus h2. And so our total work done by the conservative force in this case would be equal to mgh1 minus mgh2, or u1 minus u2. This means that if an object moves from an initial point 1 to point 2 under a conservative force, the work done by the conservative force is equal to its initial potential energy minus its final potential energy. For non-conservative forces like friction, the work done in moving an object depends on the path taken. Non-conservative forces are also called dissipative forces.